This video is about AI acceleration of hardware design using the Rapid Open Hardware Development Framework, or ROHD. And in this video, we'd like to show you a detailed demonstration of using AI to design a new ROHD component using Agile hardware design techniques. But first you may ask, why ROHD instead of a traditional hardware description language? And that's because ROHD is actually a hardware construction language, and it extends from a modern programming language called Dart. And because of this, it inherits the ability to have object-oriented programming and functional programming styles that are very powerful for describing new hardware. And these are things that you cannot get in a hardware description language. And so we have examples of what we call ROHD generators that actually inherit from other generators or compose from multiple generators. And so this kind of powerful abstraction gives us the ability to compose very, very large designs very quickly. Second, as a programming language, ROHD raises the level of abstraction by allowing for new data types. And this lets us move away from bit-level abstractions to more composable design abstractions, somewhat like the transition from moving away from assembly language code to object-oriented code. And this lets the designer work at a more abstract level and also will reduce the context window when we're employing AI agents. And we've been able to continuously add new abstractions to help us design hardware more quickly, such as new data types like the floating point class, which actually inherits from something we call logic structure, which is the composition of signals, or the fixed point class. And on these classes, we've been able to design hardware that just takes these as input types and is able to construct adders and multipliers and things like that. Another type we have to deal with protocols is the pair interface class. This is something that we extend from logic structure again, and we have a further extension of that called ready valid interface, which we will be using in this demonstration. We even go so far as to have more abstract types, more powerful types like finite state machines, or even pipelines. And so this is the level of abstraction we can get with a modern programming language like Dart, where we've embedded the ROHD semantics. Now, the ROHD framework itself benefits from large software ecosystems with modern IDEs and language servers, and even model context protocol servers that assist AI. For example, there's one specifically for Dart and Flutter. And embedded in this framework is an interactive speed simulator where tests are actually written as well in ROHD. And this is highly relevant for use with AI because it provides very rapid feedback for test-driven design. There is no compilation step, so the simulator startup is basically interactive. And this is something critical, we found for both the human designer in an Agile loop, as well as using AI algorithms to iterate on a design. Now, a second question you may ask is, why are we so focused on Agile? And Agile methods have been the key to the software revolution of the past 25 years, when we moved from a waterfall methodology primarily to using Agile. And yet we don't see these methods used in hardware that much. But Agile hardware design methods were the key to this rapid ascent of the RISC-V architecture. And if you combine a modern hardware construction language like ROHD with Agile hardware design methodology, you get a really powerful, productive hardware development environment. And the reason is because Agile design leverages the fundamental software principles of keeping your design always alive, using test-driven design, and doing feature-by-feature design evolution. And this means that you can work from a working state, go into a broken state where you're adding some new features, and then get back to a working state. And this is exactly where AI agents can help, because they can understand how to manipulate a design from a working state to another working state when you ask it the right prompts. So returning to our framework, there are other capabilities we have in the overall ROHD framework that help us with our methodology for designing hardware very quickly using AI. And a big one is the ROHD hardware component library, where we've been adding more and more components, composable components. It's been growing over time, and here's a partial list of the available components that we have for doing design and composing new designs using this framework. We also have a verification package and a co-simulation package for working with system Verilog modules as well. Let's turn our attention to our cockpit, which is VS Code, operating in the ROHD HCL repository, and I'll show you some of the features of the ROHD framework and its library of components. Now, ROHD is a hardware generator framework, and as such, it is really a software framework that helps us design hardware rather than a hardware modeling language. Some key techniques in ROHD to understand are the use of software patterns, like inheritance and generic programming, to help raise the abstraction of hardware design. Even signals or wires are abstract, such as the logic, and are rarely specified with a width, but rather we rely on the width of the logic being programmatically specified from other widths in the system. And logic structure is a heterogeneous collection, possibly nested, of logics. And logic array is a multidimensional array of logics, and interfaces are a collection of possibly nested sets of wires that can be direction based on whether they're on ingress or egress of a module. And this is really useful in designing protocols. A key starting point in ROHD is how to build a module, and we have this markdown we've created just for that purpose. This is something we would expect users to read first, and we're going to actually feed this to our LLM. Now, a module is a generator of a block of hardware, which has an API containing many of these abstractions we talked about before, and especially at the boundary where they can change the shape of the module dramatically based on the instantiation parameters, which are for the most part not integers, but other ROHD objects, such as other kinds of logics, or the interfaces, or even functions, or other modules. Now, since this is the human starting point, we actually had our LM not only read this file, but read the entire repository so that it could ramp up on the programming patterns we use in ROHD. And so this is what the LM picked up. So in terms of programming patterns, it figured out that we have, modules that can inherit from one another, that there's things called interfaces. There's configuration-based design, so we have a lot of knobs that we can change in a given component. We even have static or runtime parameter control. So it's picking up a lot of the patterns in the ROHD hardware component library that we've used. In terms of the best known methods for building a module, it picked up some of the key patterns we use. We often will only pass in the inputs to a module to help define its shape, and then the module will compute the shape of the outputs, like the bit width of, say, an add or output or something like that. It understood the basic logic types that are used internally and at the port level. It understood protocol communication using the interface, basics of signal operations, and so on. So as it read these files, and especially the module, it's prepared to build components in ROHD. And that was what we would expect a human to do, but now we're teaching an LM the best ways to build a component, because that's our exercise for today. So the plan here is to build a component we were considering building ourselves, but instead use an LM to create and test this component. And that component is a request response interface. And the idea behind a request response interface is it's a ready valid interface that takes in an ID and address request and passes it downstream if it doesn't have any memory of seeing this address. And when the response comes back, it comes back as an ID and data, and it caches the data with that address and sends it back up to the upstream interface. And so that way, if it gets another request with that address, it can immediately return around and pass back the cached data. And so this is something we wanted to build in a general way. And so we wanted to see if could an LLM help us here in building this kind of component and variations of this component. So let's consider how we would build such a thing as humans, and then we'll try to guide the LLM to build much the same way. So a architecture view of this interface would be to use some of the components we already have in the hardware component library. That would be our temptation. That basically we would take an ID and address coming in as in the upstream request, and we would check if it's in this cache. If the address is in the cache, we would then pass the ID and the data back to the upstream response, but we would have a FIFO that we would queue these things in so that we can handle other kinds of responses that are coming from downstream. Now, if we were to miss, we would send this same request down to the downstream agent, but we would also store the ID and the address request in a CAM so that when the response came back, we could actually match it. And so when the response comes back later with that ID and the data, we can match it with the address that we saw by doing a CAM lookup on the ID, store that data in the cache with its address, and put that response onto this response FIFO, and the response would eventually get back to the upstream agent. And all of this would be done with ready valid protocols throughout, so that this whole request response interface behaved in a live way with ready valid and had back pressuring and so on. So a strategy for building this interface would not be just to build the whole thing and let an LLM scramble and figure out how to build all of these pieces of logic itself, because it might end up with basically spaghetti code. We also want to reuse some of the components we already have. So we want to be able to specify some of these microarchitecture components, but not to the level of detail that we're designing it ourselves. So a strategy is to first get the API correct. And one of the ways we can go after the API is to just design a simpler form of this. And the simplest form we can think of is a pass-through, where it basically takes a request on the upstream and passes it down to the downstream. And if it gets a response on the downstream, it simply passes it back to the upstream. And that's a perfectly legal, ready, valid channel that we can build. And we'll at least get the interface right first. And that's what we would do as humans, get that interface, that API correct. So we'll teach the LLM, hey, this is the API we want, by giving it a prompt that lets it build that first. Okay, so now we're ready to give the LLM our first prompt. And we're using Claude Sonnet 4 for this. And we're going to have it build the API and actually the pass-through logic, which is just wiring in this component. So here's our prompt. So it's please create a future memory road component called request response channel that has an upstream pair of interfaces for request and response and a mirror set of downstream request and response interfaces. The component will forward an upstream request to the downstream request and forward a downstream response to the upstream response interface. And as it will eventually have some subcomponents, please add the clock and reset that we're going to need eventually for those components. So that at least our API is complete, even though it won't use clock and reset. Now, we already have these interfaces for protocols. So we have one called ready valid interface. So these interfaces will be based on the ready valid interface, and we give it the file that it can go find. And that's derived from pair interface. And that connects internal ports using a routine called pair connect IO. And so this is a hint on how to actually build the internal ports correctly and connect them to the outside world, and so that it doesn't struggle to find the programming pattern for that. Now, our request would be an unnamed logic structure. It would be comprised of an ID and an address. So we're telling it, please structure this data into a logic structure instead of just doing bare wires. And similarly, the response would have an ID and data. And the ready valid interface can operate on that logic structure as its logic type. So we're just giving it hints to try to structure the data the way we want to do it. And then it'll create the interface using the kind of data structures we want to use so that we have nice abstractions and we don't end up with a lot of flat logic as an API. So now we're going to let this run and see what it does. All right, so let's take a look at the code it produced for this very primitive component. So the first thing it created was these logic structures, which is nice because that's one of the first things we talked about was how do we want to structure the API of this. And so it created a request structure with an ID and address that's passing in. And it also has a response structure with an ID and data. And so that's nice. It used the logic structure and it figured out how to do the constructors. It figured out anything we had to do in a programming sense like cloning. So it figured out a lot of the patterns we use. Nicely, it created an abstract class for the request response. So it decided to create a module and an API. And here we have the 4 ready valid interfaces that represent the upstream and downstream as we specified. And here's the constructor. These are passed in. So this is exactly what we want to see. And then a fairly tricky way of connecting them, we give it hints to do this, of how do you connect these external signals, these external ready valid structures, right, that are signals on the outside of the module. How do you connect them to the equivalent signals and construct those signals and connect them across the port so that now you have internal signals that you can use. And it's using this paradigm we have in ROHD, which is to call a build logic function, which will be overridden in the implementation class. And so after it builds all the ports and it has the full API connected up, and it kind of has a shell, then it's going to fill in the internals of that shell when it implements it. So it's going to create a derived class. And so, well, here's the derived class. The request response channel derives from this base, which has nothing inside, just a shell. And so it doesn't have to do any of the connections because the base does all the port connections, but it has the same API. And then the logic is very simple. It's just literally connecting the data and values to each other for the upstream and downstream channels. So since we noticed that it looks like it tried to build a component and run vectors through and aborted and didn't complete, we're going to actually ask it to build another component where it has no choice. It needs to actually simulate it. And so we're going to actually have it build a buffered form of the request response channel. So in that case, it will, instead of just having straight wires, it'll actually insert a FIFO between the upstream and downstream interfaces, going in the right direction to handle the requests and responses. So here is the prompt we're going to use to create a buffered form of the request response channel and to actually get it to build us a test that we can go look at. So build a buffered version of the request response channel and use these ready valid FIFOs we have for the forward request path and for the reverse or response path. And now, so that we can look at the waveforms, let's use narrow widths for the ID and address and data and create a test which constructs a sequence of requests that fill up the forward FIFO. And then once it's full, then begin draining it on the downstream request side using the ready signal on the downstream. Just hold it low at the beginning, let the FIFO fill up, and then drop that, and then raise that ready line, and have the drain happen. And we'll use something called wave dumper to actually have these vectors captured, have the waveforms captured, so we can go visualize them. So let's get this running and see what happens. Okay, so I'll set up to look at the waveforms with you, and then we can see if it really got it correct. Okay, so let's take a look at the test it wrote. Here's the forward back pressure test that it built, and it built the interfaces very narrow. It instantiated the buffered request response channel and built it and put a dumper on it. So this is the VCT file we're going to see. Started a simulator, did a reset, and then started filling the FIFO. So testing the FIFO capacity, it starts sending in the different data items. So ID1, ID2. Let's see how big the FIFO is. It created a FIFO too deep. So it's going to run out of space pretty quickly. So basically it should be full at this point. And it's expecting that the upstream request now should be low because the FIFO became full. And then it's going to start draining. And so then it'll assert the downstream ready. It's going to turn on, and then you're going to start to see the items drain out. So let's take a look at the waveforms, and we'll have to change the window sizes so we can see this well. But we've highlighted the signals we need. Okay, so let's take a look at these signals. We see that our component is ready upstream. The request channel is ready. And we start after reset and sending in the valids. Let's put reset on there. We start sending in the valids with the request ID and the address. And we can see that eventually the FIFO becomes full. And at that point, we turn on the downstream ready so that we can start draining. And we start seeing the IDs come out as 1 and 2 with the addresses A and B on the downstream request ready. So we can see that this is now draining. And so very, very simple test, but it sure looks correct in terms of the ready valid buffering we were expecting. Okay, so now our LM has produced two simple forms of the ready valid, the request response channel. One is the sort of the straight wire through, and then the buffered form, and it has a common API for those. So now let's look at our more complicated component. This is the one we wanted to start out building, which is the caching form. And let's think about the cache form, how we would specify it as human, and how we can specify this as a prompt for the LM and see if it can get this component built and tested and running correctly. So if you think about it, this is a way you might tell a human how to build this component. You'd say, well, it inherits from the request response channel base, and it caches address requests. And so internally, this component would check if the upstream request address is in the address data cache, and if so, it would add an entry to this response ready valid FIFO on the right, So we would expect a hit to result in the ID and address matching on the data, stick the ID and data onto the FIFO. Now, if the address is not in the cache, it would store the request in the CAM below with the ID as the tag and stick the address in that CAM. So we can wait for the response, and when it comes back, we'll match it. And we also forward the request in its current form as ID and address down to the downstream agent. And so the one thing to think about is these structures are finite size, so we need to watch out for blocking and make sure we do the right back pressure. So, for example, if we miss, we have to make sure that this CAM is not full, So because we may not have a place to store the ID and address to wait for the response. So we would have to block upstream. Similarly, if the response FIFO was full, we couldn't store the hit, so we would have to block upstream as well. So we have to check, are we hitting? If we're hitting, and the FIFO is full, then we need to block. So this is what this paragraph specifies. Now the downstream response coming back, it has to block if this response FIFO. It's going to stick things in this FIFO. It's coming back with ID and data. It's going to just respond with that. So if this is full, it needs to block. But if this is valid, coming back, then it needs to tag match in the CAM and pick up the address for that ID, and then stick the address and data in that cache, and so that the next time that address is seen on a request, it'll hit. So that's the second step that this interface needs to take care of. So the downstream response interface needs to actually manage that. It needs to pair the data stored in the cache and also push the entry onto the FIFO. And that's the operation of the how we would describe it at a high level in English on a caching request response interface. And so for the instructions on testing it, we want to use narrow width, so we'll say 4-bit ID, address, and data for testing, and keep the FIFOs and cache sizes at size 8, and add waveform dumping for each test before simulations, and use the same BCD file. So that way we'll be able to look at multiple tests with the same waveform, so we won't have to spend time grabbing signals. And in each test, remember, in this architecture, the IDs are unique. So if an ID comes in, we will not see another of that ID value until that ID goes back out on the response interface on the upstream side. So just so that it keeps track of, it doesn't send in tests with non-unique IDs. And so Since this is the prompt, we're going to stick this prompt in LM and see how well it does. And it may work for a while, but it's already learned a lot from the previous things that it built. So let's see if it can go more quickly and build this, or at least not get lost in minutia that it got lost in before. So we're going to let this run. All right. It feels it's done a pretty good job of getting some of the tests running that it thinks about, has a full compiling implementation, and has some waveforms for us to go look at. Okay, so let's look at the tests that were generated by our LM for our component, the cache request response channel. And the first one it passed on was this basic cache miss and hidden. So let's just run that and retrieve the waveforms for that. So we'll run that test, and once it completes, we will retrieve the waveforms. There, and so now we'll retrieve. All right, so this is a very simple test. It has the request ready line high the whole time. It sends in a valid with ID 1 and address A, and that gets passed to the downstream as 1 and A. And the downstream passes back D as the data token, right? And that gets passed back up to the response the upstream response the next cycle. And then the task bench sends in an ID of 2, but with the same address A. And so that does not go downstream, so there's no valid for the downstream request, so that does not get passed downstream. However, it does get looked up and hit in the cache, and so you can see that the 2 is paired up with the data D that came back from the hit, and that's actually passed upstream. So this appears to be a very simple test, but it is working for the basic case of let's send one miss down the channel and store it, and then get the data stored in the cache, and then let's see if we can hit on that. And so that's a nice, very simple test for the LM to come up with. Okay, let's take a look at the next test that the LM generated, and that is a cache hit with response FIFO back pressure. So this is a test that's going to send in a sequence of hits and try to fill that FIFO by providing some back pressure on the upstream response. And so let's see what that looks like. So run that test. All right, and now we will load the waveforms. Okay, so our request line for address requests on the upstream is high, but the response is low. So we're going to try to fill up this cache and the FIFO, the return FIFO. So we send in a request ID 1, address A, and it goes downstream, and downstream returns with E as the data. And so that's going to clearly get stuck in the cache, as well as it goes into the FIFO. And it raises the valid, right? Because this is a valid return, but there's no ready. So it's not really accepted by the upstream. So it's going to have to hold it. And that in the FIFO. And so the FIFO is now filling up. And so then another request comes in with this valid for ID 2, same address. Does not get passed downstream, so there's no valid. And what happens here is the FIFO gets full. And because the FIFO is full, that request ready goes down. So we can no longer accept address requests. The system tries to send one anyway. It sends in a valid and the ID 3. It's because this is ready, this is an illegal transaction. It's not going to happen. And so it certainly does not get passed downstream. And it doesn't get into the response queue at all, right? This is just going to sit there. So this is a dropped request because it was illegal to send it in here. And the system continues to be blocked by this full FIFO, and so it tries to send in a 4, and it's holding that valid for a long time. So the 4 is not going in, right? Until we release this, we allow the upstream response to start accepting responses. And so at this point, we can start accepting a response. And of course, the first response we're going to get is that that 1 and the data token E, right? And then the FIFO is no longer full, and we're allowing more requests to come in. So the next one that's going to come out of the response is the one that's in the FIFO, which is 2 and E. That's going to come out. And then because this came up, the 4 was accepted, and the 4 hit, and so the 4 and the E come out. And so this is, you'll see a 1, 2, and a 4. The 3 was a drop transaction because it was illegally entered in the system. So kind of a nice test for this back pressure test. So the test we saw created by our LM for our caching component were nice but sparse. So they didn't really cover a lot of the design space and didn't really stress this design. So, we saw, a basic case where we had a transaction miss and then hit. So very simple smoke tests. Then we saw, multiple misses going through, and then eventually those same addresses got hit. So another sort of smoke test. Then there was another test that made sure that the CAM pushed out stale IDs and kept the fresh IDs, so it wasn't losing the wrong IDs. And then finally, that the request interface would back pressure with enough hits on a given address that this FIFO would fill up. But there's a lot that's missing. For example, we did not see a test if we have a bunch of address misses, right? They'll also fill up that FIFO with the downstream responses coming back. And then that would actually cause a back pressure on any future hits coming in. Now, it wouldn't back pressure future misses being sent downstream. So that needs to be checked out. And then simple back pressure on the downstream responses, making sure that the FIFO blocks when it fills up the downstream responses, and that ready line goes down. And then the other one that's interesting is the CAM. Why do we not fill up the CAM? Why doesn't that back pressure? We should be able to fill the CAM, and it should back pressure the system on misses. And then finally, we didn't really see a good concurrent test on this interface to the FIFO of, a hit coming in and a response coming back, and a back pressure scheme so that hit is blocked from accessing the FIFO while the downstream response comes into the FIFO. And with that kind of testing, I'd be a lot more confident that this component was really working. At this point, it's wiggling, and we really need to create some more tests for this. So that'll be our next task. Is let's see if we can get the LM to do more aggressive testing of this component. Okay, so for our first directed test, we have a prompt ready to go. And what we'll do is try to stress test the filling of the FIFO coming from downstream responses coming back. And the idea is that this should block hits coming in, but it shouldn't block any misses going out to the downstream. And it should also block any further downstream responses coming back. And so trying to fill up the FIFO just from too many responses coming back would be the interesting test case to look at. And so here's our prompt. Please create a test case for our component where we send a series of unique address requests, so those will cause misses, whose downstream responses will fill up the response FIFO and end up back pressuring the response interface, as well as back pressuring the upstream request interface, but only for hits. And that's on an address from a previous request, right? So that it's a hit. But the misses should continue to go downstream. And so let's see how well the LM does on creating this test. Okay, so we created a failing test case, and this is telling us that we have a cache that doesn't satisfy that test, and so we'll actually ask it now to please fix the cache. And so it's going to make this change. And this is probably logic we should have by inspection seen was incorrect. We saw that it's not really doing the, it's not checking for, it didn't split apart these two conditions. And now it's going to rerun all tests after it fixes this one. So you can see this is truly test-driven design. We realized a behavior that we hadn't clearly specified. We specified it using a test instead of a spec. We drove it with a test. We said, please create this test. It realized it didn't work. And because our iteration loop is very fast, it can run the simulator many, many times in an iteration loop as it's checking. It's able to verify that it didn't break anything and that the new functionality is we get it from and we have a test to match. And so that really is in the spirit of Agile design. You can see AI is in the loop helping us get the correct behavior and adjusting the functionality as we figure out exactly what we want. Okay, so the second problem that we really wanted to go after was the concurrency issue at that response FIFO, that we try to make sure that an address a request coming in, if it's going to have to go into the FIFO, loses against a downstream response that's also coming in and hitting that FIFO, and that the arbitration happens via back pressure. So here's our prompt. Please create a test case where we have an upstream request with an address that, if accepted, would hit in our cache at the same time as a downstream response is coming back and needs to be stored in the response FIFO. Demonstrate that the upstream request is back pressured and not accepted until the downstream response is stored in the FIFO. And so we'll let it work on that. So it seems to come across a problem. It seems like both requests are being accepted. Both the upstream request and the downstream response are being accepted. Okay, so it doesn't look like it solved this problem. It thinks that it can resolve, it can actually have a FIFO that takes in two requests at the same time. So we need to go take a better look at this. All right, let's try reminding it that the FIFO cannot do this. So let's see. So basically, we're going to give it the hint that, if you're seeing something coming from the downstream, you should be blocking the upstream and not letting it contend for the FIFO. And it's not clear why the logic works. It's probably arbitrarily picking the hit and then we're dropping the downstream. So let's make sure that it focuses on that. Okay, so the last area of concern, based on the first series of tests we saw and the sparsity of them, is that CAM. It's not clear to me how the CAM is going to back pressure. CAMs will just fill up, and you'll just keep inserting elements, and they'll push out the least frequently used item, just like a cache. And so what's going to cause it to back pressure? If we make the CAM small, then that could be the way we could force this. So so I'll probably give that hint. So let's say, here's the prompt. Let's create a test case where the pending request CAM fills up and back pressures the upstream request. And this was my concern. We were midway building these caching components. We hadn't thought about how to deal with counting the number of elements in the cache to make sure that we could use it as a CAM. So now the LM's going to go add an occupancy counter, which we had not anticipated. All right, so it was able to add an occupancy counter to our component around the CAM, and that way we get CAM back pressure. Test-driven design, not only did we find the problem, but it actually, LM was able to generate a solution with a local wrapper around the CAM. So we should think about how we would generalize the capability. of doing occupancy tracking in a cache, and that could mean that we need some new features, like one we're thinking about is read with invalidate. So if you store something in the cache, and then when you read it, you want to treat it as an invalidate in the same cycle, so you don't have to have another cycle to do that. That would likely be the logic we need here, and then the occupancy logic should be quite simple to push into the CAM. So we're going to go work on that next, figuring out how do we generalize our cache components so we don't have to have this this logic outside that's going to start growing, and bugs that we find in occupancy tracking will be in many places, so we'd rather just solve it for once in the CAM. So we'll go and work on that next. Okay, so we can create a CAM with back pressure. We are going to break this down into features, and since we have good tests for the associative cache, the first feature we think we're going to need is the ability to invalidate on reads, so we can do a read and invalidate in the same cycle, and so we don't have to spend any extra logic outside of the CAM dealing with that use case. And so if we look at the fully associative cache, we look at the interface of the cache. One thing we note is we have these validate port interfaces, which can contain a valid bit and wrapped around the regular data port interface. And we need another field, which is the read with invalidate field, meaning to tell it, yes, we want you to invalidate the entry upon read. So that's one place we know we're going to need to make a change. And then in the associative cache itself, if we look at how we implemented things, basically we actually use a one bit wider tag, and the valid bit is stored in that tag. And that makes it really easy, to tag match, right? You can tag match with the valid bit high when you're coming in with a read, and know that you actually hit on a valid entry. But that's going to make it very difficult if the tag is actually implemented in a register file, and in fact in a true register file where the bits are where you can only access via ports. And so since we don't want to create another write port just to update the valid bit, we will separate out this valid bit so we can have that logic just in this case of the implementation of a managing the valid bit and not having to write the whole tag entry. So those are two changes that we know we're going to make if we want to be able to do read with invalidate for the fully associative cache. So we have a prompt ready to go, and I'll read the prompt to you as we submit it, so you can see this sort of feature by feature way of doing things. So please create separate state for the valid bit of the tag rather than storing it with the tag, so we can update the tag valid bit without having to use a whole write port on the register file. And then please add a Boolean option on the valid data port interface to allow for read with invalidate logic to be passed in with the read ports. And this option, we don't want this option on the write ports, so we want to make sure that that's checked. So this will likely affect the cache itself and not just the fully associative cache. This logic has to be pushed down into that portion. And then create logic to do the read with invalidate. Make sure a cache tag matches when that valid bit is high for that entry. So that has to be a separate comparison, not just with the tag. And then if you hit, make sure you return the hit data, but also flip that valid bit to low. And so that's what we want it to do. And these are the steps we think it'll help get it to be successful. So let's submit that prompt and see how it does. Okay, now we're set to create the new option for our cache, which is occupancy checking. And really, we have some hints from the way we do FIFOs. We have occupancy checking in FIFOs. So we just want to use that logic and that API for our cache. So here's our prompt. We'll try to give it a good corner case to drive the implementation. So please add occupancy logic to our fully associative cache and make sure it's optional. Use a similar API as the FIFO for the full empty conditions. And then use a key test that a fill simultaneously with a read with invalidate on a full cache should be possible. just like we do with FIFO, we can do a simultaneous read and write when the FIFO is full. And so let's make sure that that condition is possible, and that's a pretty good robustness test for the occupancy checking. So let's see what it does with this. Okay, the LM completed this task, and we actually have now the full and empty and occupancy counters for the associative cache. Now we should be able to use this as a CAM in our cache example, the cache request response channel, and we should be able to insert this in that and remove the occupancy logic. So that's what we'll do next, so that we can use this more general component. Okay, so here's our prompt for fixing the cache request response channel by using our new feature. And we'll let this work on this prompt for a bit. Okay, it did that replacement. Let's go take a look at how it used the new feature in our cached request response channel. So in the cache request response channel, it made some edits. We'll find those. So here it generates occupancy as a feature in the fully associative cache, so it asks for that. And then it removes its own internal signals. And it removed all of the occupancy tracking code. So that's all gone. And I'm assuming that it is assigning CAM full from the CAM. And the back pressure is all working. So all that logic that it was inserting to do custom occupancy tracking is gone. This is stuff that could have ended up being spaghetti code as we added more and more features to the cache request response channel. The tracking could get in the way. Instead of just pushing it into the component, we could have just let this grow and grow and grow. And this is what happens with logic, is that this all starts to get customized. And it's what I mean by spaghetti logic. Instead of just capturing the feature as this singular, output, which is the CAM is full, and making sure that you deal with that particular protocol and not ending up kind of wandering and creating custom logic that effectively does the same thing, but starts to get wrapped up in other computations. So this ends up cleaning up the component quite nicely and on top of that, giving us a more capable component in the CAM. And so this is a very good demonstration of Agile techniques and driving tests through, and then finding capabilities that should be generalized using modularity to drive the intent of the component library. So, okay, so we're pretty happy with the functionality of the components we've built. But we need to do some cleanup, and as we scan the code, we see a few usages of syntax that aren't quite right. Like, for example, this very first one, there's no reason to use a ternary here when you can use try output. So we'll give it some hints to do some cleanup, and then we'll go and walk through some of the code. Okay, let's look at some of the results of how we used AI to accelerate Agile design of our component, the cache request response channel. This was one of the tests that actually drove some of the changes in functionality into the component. And it was this idea that if we sent in enough requests, we would fill up the CAM and the requests should block. And we found out that our CAM didn't have any occupancy counting, which we asked it to implement in the CAM. And we were able to get this test to pass. And then we did further changes to push that functionality into the CAM itself to generalize it. And then we also generalized our outer component itself. And so we'll show some of those changes, but first we want to look at this test and see how this test was actually used to drive more functionality in. Here you can see the test allocates a cache request response channel, and it has a a cam of size 4, and the response buffer is 16. So we pretty much know that the cam will be a limiter no matter what we do. In this case, we're not even using the response buffer at all. So we'll watch how this test runs. We're going to dump some waveforms in this cam full simultaneous ops file. Let's take a look at the waveforms and see what really happened. And so in the waveforms, you can see that there are 4 addresses that are requested with these 4 IDs, and these are the addresses, and they immediately go downstream. And then, so these are actually filling the cam as they go in. So we know now that the cam is full. And so it generates one more, it tries to generate one more, but the ready line is low. And so it can't send the valid downstream. This is not a valid address request. It's just basically blocked, rejected, and dropped. Then it sends in 6 and holds it. So it's holding this request to see if it'll go in. And it sends in the test structure sends in a response on ID 1. And so that's going to clear ID 1. It's going to invalidate ID 1 when it does the cache lookup. And that makes space for 6 to come into the system. And so 6, you can see, gets sent downstream because it was also accepted into the cam. And meanwhile, now that we have this response, then the upstream sees the response. And so that shows that this simultaneous access of the cam using a read with invalidate actually was successful. This feature works. So let's look at some of the code now of the components that were used in this Agile design experiment. So this is the final form of the component that we were trying to build. And you can see over time we've built up a much stronger API. We have our original address requests and response interfaces. And then we have a cache factory. And this is the you'll see that this is for the data address cache. This is a way to build the data address cache. And so here's the function that can build it. So as long as you supply a function that returns a cache and takes these arguments, you could use any cache you want as your data address cache. So this is a generalization using what some people in programming call a functor to during generation time give you more flexibility for this component. So now you can pass in any kind of cache you might be able to use for that data address cache. Similarly, the cam, we're using, we just have one cam, the fully assistive cache, but it can take in different kinds of replacement schemes. And so here is the replacement scheme that we're passing in. And it's another kind of functor, right? It's a replacement policy function, and it just has to have this signature. So any replacement policy you come up with, as long as you can supply the signature of hits, allocates, and invalidates the number of ways, then that's a function that, as long as it generates the logic for replacement policy, you can use it for the cam. And then, of course, the basic parameters, the FIFO size for the response buffer is 16 by default. The number of ways in the cam is defaults to be 8, and so on. So that's a fairly general API for this cache request response channel, right? Where we can actually configure some of the components to have different functionality. It can be a completely different kind of module as long as it has the same base, the cache, or we can pass in functions like the replacement policy that modify behavior of an existing component that we have. So you can see this is very influenced by software programming to enhance this polymorphism of this module, because during generation time we can take advantage of all the software techniques to make this a completely general generator. And this is the build logic. Basically, this is mostly the instantiation of the core components. Here's the address data cache. This is the cam. It's calling it the pending request cam. This is the FIFO, the return FIFO, response FIFO. So those are the instantiations. And then it separates out the cache logic that connects these things, because there's some gates, some logic that has to interconnect them. And this is the section where the code is, the logic is generated to connect things. So for example, this was something that was really complicated in the past. Now it's a single line, which is, does the camera turn full? And yes, we just access the full line of the associative cache we have instantiated. The rest of this logic I won't read through, but this has all been tested against the variety of tests that the LLM generated to make sure that all the different descriptions we had of the way this component is supposed to work, they're satisfied with tests. And so this is the logic that it generated. And so you can see fairly readable code. We can walk through and understand every piece of it quite simply. Okay, so let's look at one of the subcomponents that was also modified during this exercise, which was the fully associative cache. And in the cache, we saw that we actually wanted to push some of the functionality that we had tested in our cache request response channel into the CAM because we were using occupancy counting on the outside. So here we actually have the result of pushing this functionality into the component so that we could be reused, and the generate occupancy Boolean is here, and then these are the outputs of occupancy that would be computed if that was true. And here you can see by default it's not turned on, so it's a optional logic that we can turn on, and then the outputs are also produced as well for that feature. The other feature that we added was the read with invalidate, so we'll see some of those changes here as well. Here is the read with invalidate logic that checks to see if we can actually tag match and send the data on the read port, but also invalidate the valid bit of the entry so that we don't have to actually go through a cycle later or use a write port to modify that bit. And so this logic was inserted. And along with that, there was some changes to the fact that the valid bits were separated. So here we pull the valid bits out, and they become their own state that is managed by both the write port, which sets the valid bits, and the read port, which can potentially both match on the valid. It checks the valid is high when it matches, and it can invalidate. And so that's what this logic is done. That was inserted by the LLM. And finally, we need to do the occupancy counting, and here we were able to just use our count library function and generate the flags, the values, the occupancy, full, and empty values, counting up those valid bits and keeping track of how full the CAM is. And so that was enough to provide back pressure, and we had a good system test for that with the cache request response back pressuring based on that CAM being full. And so now this component also has its own tests for the occupancy counting, but that was a nice system level test to have to help drive the functionality into this component. And so using AI in the inner loop of Agile design, we were able to actually, make assertions about what functionality we wanted, incremental features, and it would generate not only the change that we wanted, but also the tests that helped drive that change and validate it. And at the end, we're left with components that are quite modular, have good APIs, and they also have tests. Tests that we thought of to generate like corner conditions that help actually build out the design and later make sure that it stays healthy so we can refactor without breaking those edge conditions. And so this is a really good example of using an LLM in the inner loop to drive Agile design. And since Agile design is really about doing things feature by feature and keeping things always alive, and doing incremental changes over time as opposed to having everything happen at once, this is a really good fit for AI because AI likes to operate in a smaller context window. It understands locally what you're talking about much better, and we found this is a very effective way to accelerate Agile design using the AI engines. Great. I know that LLMs are often very happy with what they do, and they sometimes promise things that they didn't actually accomplish. But in this case, I feel much better about the coverage that we have for the cache channel that we have, the cache request response channel, and the fact that we held to modularity by pushing extra logic that could be reused into a component we thought was done, which was the fully associative cache, and we'd forgotten to use to create an occupancy counter, and now we have a full set of tests for both that component on that new feature. So we did, basically feature by feature test-driven design for the cache, as well as drove much more correctness into the component we were building by describing English level tests that we knew were corner cases in this smart architecture. So this is a really good demonstration of how we think Agile design can be accelerated using AI, and especially in the road environment where we have access to an advanced programming language to keep the abstractions high and the amount of code small, so we have a nice small context window. And we have access to an integrated environment with a built-in simulator, which really helps the LM learn what it's doing and check its results very quickly and iterate. And so that's one of the reasons why we were able to do this component so quickly.